So tonight we're going to talk about cybersecurity and graphs. The graph community's slogan, if you've heard it maybe, is that graphs are everywhere. And as you start to get familiar with graphs, you start to realize that it's true. And cybersecurity is no exception. So I'm Eric Spiegelberg. I'm a senior consultant with GraphAware. I'm a Java software architect and developer here in the Minneapolis area. And I lead GraphAware's research and development of applying graphs to cybersecurity. I think at GraphAware we have a very unique perspective on cybersecurity, the type of research that we're doing, because we're software developers who have graph expertise, researching security, rather than security researchers pursuing software development. GraphAware is a small global software consultancy with members in the US, Europe, and the Middle East. And we offer consulting, training, and software development centered on all things graphs and Neo4j. We're also a Neo4j solutions partner, and we develop open source and commercial tools, frameworks, products, and are frequent sponsors and speakers at graph conferences and meetups around the world. So just a general overview of the presentation. I'm going to be giving some background on cybersecurity. We're then going to discuss Meter, which is a US government-backed R&D center whose mission is to advance technology. And then Meter has developed two specifications we're going to discuss, Styx and Taxi, which are rising stars in the world of cybersecurity. We'll then cover an example attack scenario, which will lead us to a demo of GraphAware's Cyber Threat Server, and that's a Taxi microservice implementation that we're currently developing. Along the way, we'll also do some graph exploration using Cypher and the Neo4j console, and then we'll wrap things up and be available for questions and further conversation. So defining cybersecurity is surprisingly difficult because it is a vast topic that can mean many things to many people. And each aspect of the topic is deserving not only of its own presentation, but probably of volumes and volumes of books on each aspect. For now though, we'll go with this definition on the slide, which is that cybersecurity is the technologies, processes, and practices designed to protect data and systems from attack, damage, or unauthorized access or use. So who's affected by cybersecurity? They say a picture's worth 1,000 words, and with this picture we're trying to say that we think everyone is affected. In fact, we think probably there's no one that is not indirectly or directly affected by it. So needless to say, we at GraphAware think that the importance of cybersecurity is hard to overstate. So other than the little detail that it affects everyone, why is it important? And it's because technology is now omnipresent. It's woven into almost every aspect of our daily life. And examples of why it's important run the full spectrum, from being trivial all the way to the other end of the spectrum, being gravely serious matters of life and death. So examples of trivial are the text that I personally send every couple days to my friends to coordinate my plans for lunch. So while they're trivial, I expect that they're private, as they're only intended for the intended audience of my friends and I. At the other end of the spectrum, there are vitally important cases that form the foundation and freedom that enable human rights and freedoms around the world. Some governments exploit a lack of effective or high adoption levels of cybersecurity to their benefit, and they use that to oppress and suppress their citizens. So these both ends of the spectrum are equally important because security is layered and it's only as strong as its weakest link. So you can't fully protect the important things like people's personal freedoms and human rights if you decide to selectively protect those things and ignore the silly trivial things like my lunch plans that I send and organize over lunch. So to have effective cybersecurity, the whole spectrum needs to be equally protected because it's often on the same devices, whether that's your mobile phone or your computer or just the internet in general, that are used both generally by consumers and world leaders alike. So if those two groups and everyone in between are using the same communication platforms, those platforms need to be secured as if everyone is a world leader. So now that we've covered why it's important, I'd like to talk about the impacts of cybersecurity. And originally I had multiple slides here that discussed famous examples of viruses and worms and data breaches and lapses of security. And tonight, in the interest of time and focus, I've taken them all out. Because I found myself, once I started talking about it, that it became a black hole of conversation. And I would just go on and on and on. It was just too difficult to pick and narrow it down to a handful of prominent examples. So while we could spend the whole evening discussing these examples, instead I've tried to distill all those slides just down to 3 data points. So how many people here use Wi-Fi? Everybody uses Wi-Fi. And unfortunately, the security protocol that protects Wi-Fi has been broken. So Wi-Fi in general is now considered insecure. Considering that basically everyone uses Wi-Fi and the frequency with which they use it, that's actually a pretty big problem. The second data point is that hackers in 2017 stole an estimated $172 billion with a B. And that's just a mind-boggling number. And our third data point is that the VP of Privacy and Security at Google has publicly stated that the threats to our most personal data, our businesses, our infrastructure, and our democracy are real. And that's a pretty scary statement from a person who probably really knows what they're talking about. So I like to often characterize cybersecurity as the global warming of IT. And that's because it's a critically important topic, but it's invisible and it's intangible. So it's hard to raise the alarm, and it's hard to get people to engage or act, because it's just simply too easy to shrug it off and put action off either until another day or to leave it up to someone else. So I couldn't resist adding just one more slide on why cybersecurity is important, and that's because there's more to life than just economics. Cybersecurity is now the foundation of global human rights and freedoms. And as I mentioned earlier, various governments around the world use a lack of cybersecurity, and they exploit it to their advantage to oppress and suppress their citizens. Another example of human impacts of cybersecurity is some guy named Edward Snowden, who you may have heard of. We all know he exposed that the US government was surveilling both US citizens as well as non-US citizens around the world. And so while there were other factors in play, what really enabled that situation, at least on a technical level, was the lack of adoption of effective cybersecurity. If every email and every phone conversation were encrypted, then the US government wouldn't have bothered to collect the content or the metadata of these conversations and communications, because they just simply wouldn't have been able to do it. So speaking broadly, there's some global trends that we're seeing within cybersecurity, and unfortunately the state of cybersecurity seems to be trending downward. What we're seeing is that the frequency and sophistication of the attacks are increasing. We're also seeing a trickle-down effect where even the lowest level of cyber criminals are gradually adopting the advanced tactics, techniques, and procedures of more sophisticated groups. Sometimes those groups are other more sophisticated cyber criminals, and sometimes those groups are actually government-sponsored state agencies. So the thinking that it's okay for governments to do hacking or surveilling unfortunately comes with these unforeseen consequences, because these tactics and techniques ultimately trickle down and are being observed and adopted by cyber criminals. This leads us to a situation where it's a perpetual game of cat and mouse with ever-increasing stakes and consequences. So I think it's fair to describe cybersecurity not as a war that's ever going to be won, And instead, the situation is that realistically, the goal is to just get ahead of the bad guys and then try to stay and maintain that lead for as long as possible. But all hope is not lost. Governments and industry are mobilizing, working on these challenging problems, and trying to gain these advantages to get and stay ahead. One of these groups is named Meter, and it's a US-based, not-for-profit that's sponsored and funded by the US federal government. So Meter operates federally funded R&D centers, focusing on numerous areas of industry, and their charter is to work for the public benefit to advance technology. Within their cybersecurity efforts, Meter has recognized graphs as a key technology enabler for advancing cybersecurity. And this is due in large part to the shape of the cybersecurity data, which is high volume, unstructured, dynamic, and highly related. And it's these characteristics, as well as just the sheer volume of the data, that has transformed cybersecurity into a big data problem. While each of these attributes is certainly important on its own, it's this last attribute of being highly related that's of particular interest to us as people being interested in graphs. What does it mean when I say cybersecurity data is highly related? So imagine that you have a system that's under a denial of service attack, which is where malicious parties attempt to overwhelm your system with what otherwise would be legitimate requests. Now imagine that there are thousands, maybe tens of thousands of these servers barraging your system, each submitting hundreds of requests per second. The end result of a denial of service attack is that your system's going to become overwhelmed, and eventually it's going to slow down to a crawl to where it becomes unusable if it just doesn't crash immediately right away. The metadata for each one of these requests, such as the source IP address of where the request originated from, needs to be digitally captured and associated with the attack for later analysis. So I jumped ahead a slide, but I'm trying to associate the IP addresses of each one of those servers. As you receive those requests, you want to capture where that's coming from, and you need to store that for later analysis to try to figure out, who's behind this denial of service attack. So connecting this metadata back to the attack then forms highly interconnected structures, which are relationships. And these structures then fit the very definition of a graph. Interestingly, many of the individual data points, such as the IP addresses from these individual servers, are actually of very low value themselves because there's just so many of them. If you find yourself under a denial of service attack, you're just going to be overwhelmed with an ocean, with wave after wave of these requests. And knowing just a specific IP address that one of the requests came is just meaningless because it's a drop in the bucket. So while the individual IP addresses are of low value, it's the relationships between the IP addresses that can lead to an insight, such the fact that the addresses are all from the same domain, or maybe they originate from the same geographical location. It's these relationships that are the very strengths of graphs and graph databases. And this is why Meter and others recognize the power of graphs. So along with recognizing the power of graphs, Meter also recognized that a common language was needed to exchange this cyber threat intelligence data and developed the Stix specification. So in short, Stix forms a standardized schema or language to digitally describe this attack information. Stix 1.0 made use of XML, and the recently released Stix 2.0 makes use of JSON. Stix enables organizations to efficiently and effectively produce, share, and consume this cyber threat intelligence data with one another in a machine-friendly format. Having standardized the format of the information, the attack information with Stix, Meter also recognized the need for communicating this information in a standardized way. So they created a companion specification named Taxi. While Taxi does support some other forms of communication, at its core, Taxi is a REST server that supports the creation, reading, updating, and deletion of cyber attack information, as well as providing pagination, sorting, searching, and versioning. So those that aren't familiar with REST, it's a simple method for interacting with computer systems by sending small requests and expecting a specified response. So for example, a web browser is an example of a simplified REST client. When you're going out and getting a web page, essentially you could say that that web browser is serving and acting as a REST client. So this standardized communication now allows organizations to share and consume the Styx data with others very easily. So admittedly, as a software developer, when I started to learn about Styx and data, my initial reaction was to shrug a little bit and say, well, it's just JSON and it's just a REST server. There's really nothing magical that's happening here. And as I started to learn more about the cybersecurity landscape, what I learned is that in the absence of these two standards, it's up to individual vendors to make these specifications. And as you can imagine, there's lots of competition, which isn't necessarily a bad thing, but it also leads to interoperability and just increases the overhead and the difficulty of sharing. So as you learn about cybersecurity, you learn that there's, in real life, government agencies that can't talk to each other even though they have the necessary information because they don't have a standardized way of not only transferring it, but also just representing it. Styx and Taxi, their goal is to change that. And so while they're just JSON and a REST server, it's the fact that they have the full backing of Meter and the US federal government. They have this 800-pound gorilla behind it. And so the whole industry is organizing, and that's what's leading to the adoption of Styx and Taxi. So this brings us to GraphAware's Cyber Threat Server project. GraphAware agrees with Meter that graphs are the foundation of cybersecurity's present and future. So we're pursuing the development of a Styx and Taxi implementation. It's a microservice style architecture powered by Java, Spring, Spring Boot, and the Neo4j graph database. So more details about our GraphAware's Cyber Threat Server will become available as we publish them on our blog or website, as we release them publicly, or if you wish to engage us to learn more, just feel free to send us an email at info@graphaware.com. So let's walk through an example attack that illustrates Styx, Taxi, GraphAware's Cyber Threat Server, and ultimately graphs using the Neo4j database. So our attack scenario will make use of the Poison Ivy malware. Poison Ivy is considered to be the Chevy pickup of malwares, in that it's incredibly common and just sees incredibly widespread usage. Once installed, Poison Ivy allows someone to remote into a compromised Windows machine, and from there, that attacker has full control of that Windows machine and can do anything they want, such as extract any information that's on there, or in turn attack other machines. Poison Ivy is currently for sale on underground markets, and so it spreads virally as people discover and rediscover its utility. In fact, it's so widely used that security professionals have a very difficult time tracing attacks of Poison Ivy to any particular threat actor. So that's a great example of the difficulty of analyzing cyber threat intelligence data, and we're going to use that for the basis of our demo. So our attack scenario is going to be a phishing scam, where a malicious threat actor, or that's a synonym for basically the bad guy, they're going to send an email to someone, baiting them into opening the attachment and executing the contained file, which then installs Poison Ivy on their machine. And from there, the threat actor can assume control and do whatever they wish with the machine. This diagram here just gives a visual depiction of what I've just talked about. We've got our threat actor up at the top. Over in the left corner, we've got an identity. And this diagram represents Stix, a Stix representation of real-life attack information. So threat actors like to make things difficult. They like to remain anonymous. They like to throw people off their trail. So they often have multiple identities. And cybersecurity analysts have to attribute any attack not only to the threat actor, but to what identity the threat actor's been using. Threat actors also use attack patterns. It's how they approach attacking you. In our case, they're going to be using this phishing scam. And then, of course, as we've mentioned, in our particular case, they're also using the poison ivy malware. And so for those that can kind of see where this is going, although it's not circles and lines, it's boxes and lines, which is a key telegraph that we're heading somewhere that is going to, graphs are going to be involved. This diagram is essentially the beginning of a graph. So the data I'm going to use for this demo is publicly available at this URL. So we'll go ahead and visit. It's data actually from the Styx 2.0 example website. So if you scroll down, you're going to find that there's a particular port here related to poison ivy, and we're going to use this poison ivy JSON. I've already got that open in this tab. And so what we're looking at right now is actually Styx data in JSON format. So the first object is of type malware, which we've discussed. This is the poison ivy. That's its name. And then it contains various information about this particular variant of poison ivy. Just below the malware object, the second object is the identity, and this is referring to the identity of the threat actor. So this sample JSON is about 2,500 lines long, which for computers is trivial. For human consumption, it's far too long, so we're not going to go through any more depth scrolling through it. Had we gone through there, we would find the threat actor and also all of the pieces of that diagram that we've already discussed. So cybersecurity is a huge, complex topic, and a single attack could generate gigabytes, maybe even terabytes of data. So we're going to have to constrain the demo a bit because to a little bit of a contrived scenario, because real life is just too complicated and too verbose to put into a live demo. So our demo scenario is going to have two parts. Part A, we're merely going to talk through what happens after an attack for an organization that's been hit by poison ivy and they wish to share that information with their partner organizations. And then part B, that's when we're actually going to be a different organization that wants to sift through and consume that Stix information using Taxi. After we do that, then we'll actually use the Neo4j browser to write some cipher statements and sift through that Styx Taxi in graph form. So as I said, we've got our third-party organization, cleverly named Organization A, that's been attacked and infected by poison ivy. So where we're coming in, they've already cleaned up the mess. They've done all the right things. They've defended themselves. They've shut down the attack. They've done their root cause analysis, their disaster recovery. They've patched their servers, all that good stuff. Now what they want to do is they want to kind of pay it forward and provide that information and share it to other people. So hopefully that they can avoid the same pitfalls of the attack. Maybe they can see it coming on early, or if they don't see it coming early, maybe it will help them defend against it. So what we're going to do is we're going to take the JSON from our sample, which we're seeing here, and we're going to use a REST client and submit it to an instance of GraphAware's cyber threat server. So I'm going to be making use of the Postman REST client. This is a freely available REST client. Anyone can download some of it. One variant of it is a plugin or an app for your Chrome browser, or you can download it for a standalone version. So I've already done a little bit of setup. I've gone through and entered my credentials to interact with GraphAware's cyber threat server. I've put in the URL of the cyber threat server that's running on my machine. And I've got a console right here where the cyber threat server is running. So I'm going to clear that out. And when we go back and submit this Styx data, GraphAware's cyber threat server is going to receive the request. It's going to parse all of the Styx information, convert it into a graph and store it with Neo4j. So organization A, which has created all this data, comes to the Postman REST client. And let's see if I can, like to show the console. There we go. And they're going to use the Postman REST client to submit this using a post to the well-known URL that's been shared across our partners. And we're going to click send. In the background, you saw a bunch of stuff fly by from the cyber threat server. And it was, as I said, that was processing the Stix information, turning it into a graph, storing it in Neo4j. So if I expand this a little bit and scroll down, what's happened now is that GraphAware's cyber threat server has returned a taxi response. So there's not a whole lot of substance to this response. You can just see it says that the request was complete. We submitted 168 pieces of information. All of them were successful. And then probably the most important part of what was returned is that for each one of those pieces of information that were successfully created, it returns a new unique identifier just for that piece of information. So what we've just done is that organization A has taken that Styx data and published it to the taxi server. Now some other organization, perhaps one cleverly named organization C, is interested in consuming it. So there I'm going to demonstrate we're going to use the Postman REST client to turn around and query the exact same information that was just submitted. So I'm going to use the exact same URL address, but this time we're going to issue a GET request. And when I go ahead and do that, the response has been returned. And what we're seeing here is the exact same Stix data that organization A just uploaded. So this is an example of how Stix and Taxi enable the efficient and effective sharing of cybersecurity information. Not everybody's always going to be interested in like the full information. This is all the same 2,500 lines that we submitted. And so Styx Taxi offers a whole host of other functionality. Very quickly, one of those is the manifest endpoint. So we're going to issue a GET request to the same address, but this time to manifest. And by clicking send, what we're returned is just a high-level summary of all of that same information, minus all kind of the depth. This allows organizations that are interested to take more of the summary and work with that, for example, to just maybe determine what's new, what's changed, what's new since the last time they interrogated this taxi instance. So as we talked about, every instance of cyber threat information is assigned a unique identifier, which I've highlighted here. So of course, we could look at this date that it was added, and maybe that's more recent than the last time we hit this server and got this information. So maybe the organization we're a part of is interested in finding out more about this particular instance. So the taxi specification allows you to use the exact same URL, but this time to post the unique ID of the entity that you're interested in. So we're going to issue a GET request to that address, and by clicking send, what's returned here is the fragment that represents just this entity. Whereas before we were drinking from the fire hose and got the whole shebang, this is just kind of a much more narrowed and focused slice of what we're interested in. So like I said earlier, as a software developer, I scoffed a little bit initially, thinking that this was really no magic here. It's just JSON, it's just a REST server. But as I said, gradually the realization set in that before this, it's left to ad hoc, implementation by implementation, vendor by vendor. Styx and Taxi make a universal format that the whole cybersecurity industry is now mobilizing around. So because we know that this information that the GraphAware cyber threat server under the covers is powered by Neo4j, let's go ahead and take a look at the Neo4j console and actually see what happened with that Stix JSON data when it was put into Neo4j. So we're going to issue a very simple cipher statement. For those that don't know, Cipher is the query language, not only of Neo4j, but it's been recently open sourced to a group I believe called Open Cipher, and it's now becoming the de facto standard and widely adopted across all graph databases. So this cipher statement is going to say match anything in the database and return it. So what we see here is a visual graph representation of that Styx JSON data that we submitted to the taxi server. For those that haven't seen the Neo4j console, it's pretty cool and it's pretty powerful. It's in your browser. You execute a cipher statement up here. You've got a legend that tells you information about the nodes, what labels and metadata you're seeing in the screen. And this also allows you to change the color coding of specific nodes that you're interested in. So it allows you to adapt and color the visualization any way that adjust it to any way that helps you understand your problem. You can also drag nodes, move the graph around. So if you become interested in this node, it's funny how it gets a little squirrely at times, but it settles down. And this is how you query and interact with Neo4j. So I think it's worth pointing out here that the graph representation of the Styx data that we submitted has 92 nodes and 278 relationships. So when I said earlier that cyber threat data is highly relational, I think this is a good illustration of that, because we've got an entity to relationship ratio of approximately just under 1 to 3. So every node has just under 3 relationships to some other node. And of course that makes sense because the picture we're looking at is pretty dense. The lines in the background are all relationships between the nodes. So just to summarize, part A, organization A was attacked. They cleaned up the mess. They created Styx data and they submitted it to a shared taxi instance. So now we're part of an organization that shares that taxi instance with them. And our system administrators have noticed that our network has a high volume of suspicious outbound traffic to a specified IP address. And this is suspicious and it raises some red flags and it warrants some investigation. So because our organization shares this taxi instance with these partners, such as Organization A, we now have a go-to one-stop shop where we can investigate and see what's happening with our partners and our allies of what they're seeing in terms of cybersecurity, so we can investigate. So we've got a couple options to investigate. The first one we just saw, which is using the taxi server and a REST client to interact and send requests to the taxi server. So since we've already done that, we'll take the alternate option because we also know that, at least for this demo, that underneath the taxi server is Neo4j. So let's write some cipher queries to investigate this. So we're going to take this suspicious outbound IP address on the slide, and we've created this cipher statement. What this cipher statement is saying is find all of the indicators, which, as the name says, is an indicator of a pattern that represents the detection of suspicious or malicious cyber activity. So we're writing a query that says find all indicators where the indicator's pattern contains this IP address and return it for us to see. So we'll go and execute this in the Neo4j browser. So when we run that, we get 3 hits, 3 nodes. Ideally, we were hoping for 0 hits, because the fact that we've gotten some hits is actually a bad sign. It's a sign that that IP address has been involved with some suspicious or malicious activity. So this is discouraging. But I guess the fact that we have the information is better than not having it. So from here, we can investigate a little further using the Neo4j browser console. As we hover over each node, we can click on it, and then we can use the console to expand, and we can visually look through all of the information contained on the node. That's pretty hard to read, and it's also pretty dense. But yet, it's wonderful to have all that information there. Neo4j, the browser console, also allows you to view this exact same information. Rather than in this visual form, we can hit table and see everything a little bit more human readable in table format. And you'll recognize that it looks very similar to JSON, and some of it in fact is JSON stored from the Stix. So the Neo4j browser allows us to do a little bit of an ad hoc query and exploration. And so let's say we're interested in this particular node. By double clicking on it, its siblings, its immediate siblings, pop up into the visualization and allow us to drag them around and move them any way that we want so that we can kind of continue our exploration. So we can just do this similar with the other nodes. And if we had a larger data set, we could just go on and on and on to any depth that you're interested in. And this is a perfectly valid approach, but it has a couple drawbacks in that it's not really a repeatable strategy. It's kind of a hunt and peck following, hunt and peck searching. And so we discussed earlier that if this particular node had 100 or thousands of siblings and I double clicked it, you would get all hundreds or thousands of those siblings showing up in your visualization. And so hunting and pecking is perfectly fine, but you might peck into something that then you totally lose the context of what you're searching for. So what we can do is we can go back and revisit, and now that we know there's a trail to follow, we can investigate further by writing a little more sophisticated cipher statement. So this cipher statement says find all indicators whose pattern matches this IP address, and that's what we had done previously in the last step, and follow the relationships to return what I like to call the food chain, and in which is essentially just what it's related to. So this query is going to include the indicator, the malware, the attack campaign, the threat actor, their identities, and return it all to the visualization. So let's execute this. So what's returned are these results. So again, this is kind of a good news, bad news situation. The bad news is that the IP address we're seeing on our systems are related to a malware situation. But the good news is that we have Styx Taxi, Graphs, GraphAware's Cyber Threat Server, and Neo4j so that we can easily explore this information. So this result tells a story. And from this image, you can gather that the IP address that we're seeing has been involved with, has been captured as an indicator 3 times, and that's what these gray nodes at the bottom indicate. So you can follow these relationships and you can see that it indicates an instance of malware. That's what these purple circles near the bottom are. So if we hover over it, you can see that they're malware. We see that in the lower left corner. And if we explode that, expand that, and look at some of it, the details, we can find that its name is a particular variant of PIVY, which is the shorthand code, of course, for poison ivy. So we could continue our exploration and do the same thing with the other malware instances. The other thing that this picture tells us is that these malware, these purplish colored nodes, are associated with 2 different attack campaigns, which are the green nodes. So you can see their label down in the lower corner that they're attack campaigns. And we can just keep going up the food chain in that these attack campaigns are both associated with this particular threat actor, and then this threat actor has 2 separate identities. So from this, you can unfortunately conclude that your organization has been infected with 1 to 3 variants of poison ivy, all caused by the same threat actor. So as I mentioned earlier, poison ivy is so commonly used that real-life security researchers have a hard time attributing any instance of a poison ivy attack back to any threat actor. What we've done here is we've used Styx, Taxi, a REST client, GraphAware's Cyber Threat Server, Graphs, and Neo4j to do exactly that. Take an IP address and traverse it all the way back through that cyber threat data and actually attribute it to a specific threat actor. So while we used a very small sample data set for this demo, and it may seem like a contrived scenario, the principles it demonstrates hold true for scenarios where the scale of the data is vast and incredibly large. So essentially in this demo, we have solved what is an actual real challenging, difficult problem in real life cybersecurity. So to draw things to a close, cybersecurity is a significant global issue that has become a big data problem. Graph databases are an excellent fit for this data, with the graph's value thriving and only increasing the more complex and the larger the data set is. Tools and groups such as Meter are creating tools and specifications such as Styx and Taxi. They've embraced graphs to help tackle these challenging problems. And GraphAware, interested in all things graphs, is actively exploring the application of graph technology to cybersecurity. Thank you.